technology. These are issues of our time. And already Feynman said there is not only space in the astrophysics, there is also space in the little, in the very little, which means materials with structural elements smaller than 100 nanometers. We call nanomaterials research. I will show you in my presentation that the particular properties which are normally typical of the nanomaterials, they are also typical of micro, or let's say submicron materials. So it's in most cases enough to reach 1 micron and less to have to reach very nice materials properties, not only mechanically but also others. And this is the focus of my work. I will emphasize here the functional materials. Okay, there was a prominent presentation in this IAEM society no long time ago from Professor Gleiter. He introduced to you the nanostructured material. He was in fact the pioneer doing that field. But his principle to produce the nanomaterials was a bottom-up. He looked for the single atoms, and by inert gas condensation, he could make rows of and planes and cubes of little atoms up to 10 nanometers cube one side, and then consolidated this thing. There are also other ways to reach nanomaterials to larger scale, which are based on bottom-up principles. This is electrolytic condensation. This is, of course, ball milling and crystallization from the amorphous state. But in most of these cases, you start with the small and you have to consolidate them. You have all the disadvantages to only make small samples. You can only achieve small samples, and also have the disadvantage with all the dust and dirt between the grains at the single crystals. So it's not a very clean method. Much more clean method is if you approach a top-down way to produce the materials. So we start with a big block, the sample size we want, and then we make plastic deformation and always keep the shape of the sample. And by iterative plastic deformation steps, we bring in lattice defects. We collect these lattice defects and build up grain boundaries out of them. And this method is called severe plastic deformation because it is clear to get very small grains or crystallites, it's necessary to establish a high density of grain boundaries. And with that, you need a lot of building units for these grain boundaries, mostly dislocations. And this can be only reached if you drive plastic deformation to very, very large strains. And this is now, it was the issue how to get these very large strains. And this problem was solved by the group of Valiev and others starting in the 90s last century. And I jumped on this stage and could develop a lot together with the Valiev group and other group coming up in the early. That's why I have to explain how we can achieve very large strains. And and the issue is you have to look, you have to put your sample in some cage. You have not to deform it freely in a universal testing machine. You have to press it or to deform it under a certain constraint, because which is a very important issue of the plastic deformation, which is called severe plastic deformation. To reach large strains, you have to suppress the cracks, and this can be only done by enhance the hydrostatic pressure component in this deformation. This is done in the most popular severe plastic deformation method. This is equal channel angular pressing. Maybe it's known to you. The constraint is that the sample cannot go to the side normal to the deformation axis. This is a method which allows for the realization of samples up to now 100 centimeters in diameter. We are quite proud. We have a partner in Austrian Institute of Technology who is able to do such large samples with very, very small cracks. more scientific method, but also achieving samples now up to about 10 centimeters in diameter and up to 5 millimeter in thickness is the so-called high pressure torsion method. Whereas the constraint here, you start with the red colored sample here, you put it in between two anvils, an upper and a lower anvil, and then it increase the hydrostatic pressure because the sample cannot go to the side. The hydrostatic pressure is loaded more or less elastically. But when you start to rotate one of the anvil relative to the other, you can deform the sample by torsion because the sample sticks because of friction to the lower quiet part, and it also sticks to the upper rotating part. We can also change that. Or in other words, you make a very small sample, a thin, also not small, but a thin sample, applying a torsion test under hydrostatic pressure. And the nice thing is you can increase the hydrostatic pressure not only to 1 gigapascal, like in the equal channel angular pressing, you can increase that to several gigapascal, up to 10 gigapascal. And at the moment, we have no limit in deformation. Our deformation is 100,000% or more. It depends what you want at the end. For the industry, interesting is you can take a simple rolling equipment and you cut the sample. So you roll the sample, cut it in the middle, make a stack and roll it again. This is another kind or facet or variation of the severe plastic deformation method because it is an infinite process. You have always the same initial thickness and also the final thickness. This is for application in industry and is already used from the company Audi, for example, in Germany. Okay, also the key is you have to dramatically increase the hydrostatic pressure. Then there is no limit in plastic deformation. That's why there is no limit in making small grains except physical limits. This means annihilation of dislocation. You have, of course, to ensure that the dislocations will be accumulated, not annihilated. In that case, you can make grain smaller and smaller, and you can drive the process even to amorphous material. The effect of pressure is nicely shown in this picture. In the upper part, you have EPST pictures. It means the color is the orientation of the crystals. First, you have a single crystal, then you go to the right. Please look at my mouse ticker. And then you see the orientation breaks up in smaller island and smaller island, and the more deformation, this is here 14,500%, or even more, 14,500%. You get smaller grains, which are in the order of several 100 nanometers. The black points symbolize the grain boundaries, or in other words, the units of the grain boundary in case of deformation-induced materials. These are the dislocations. When you increase now the hydrostatic pressure, from physical reasons, you can accelerate the process of grain refinement. With the same deformation degree, you get even smaller grain and the smallest at the end. So the pressure is really one of the tools to make the grain small and suppress dislocations from annihilation. With that, people in the last 10 years had big successes. We have many, many publications, thousands of, and we are one of the field, the SPD achieved materials are one of the really high lighthouse projects in the world, not at least because of the very, very excellent mechanical properties. You can increase the strength by refinement to 10 nanometers of materials grain size. Factor 2 in titanium, and compared to undeformed copper, also a factor 2 in copper. There are several examples. All the plastic deformation conventional one are here given in the strength ductility diagram in the gray field, and all the SPD materials are beyond this limit of this banana curve, we say always. But there are not only hardening and ductility advantages. There are also other advantages. We can now make mechanical alloying not in powder, but in bulk massive materials. We can, by applying this high pressure, we can make a highly immiscible system miscible. This is an example where you see the atom probe spectroscopy picture. In the case of iron in copper or copper in iron, you can mechanically mix about 20% of iron in copper and vice versa. It is shown in this picture. And by this potential of the SPD to enhance the diffusion and mechanical alloying capability or the capacity ability, you can also change phase diagrams, at least in non-equilibrium case, but in many cases you can live with this non-equilibrium, thermal equilibrium, you can modify the phase diagrams. And so not only make more solid solutions, also other phases are enhanced in most cases to form. My issue here is to show that also functional properties can be improved by the application of severe plastic deformation, making bulk nanostructured materials. Or in other words, the bulk nanostructured materials show really benefits in thermoelectric properties, in hydrogen storage properties, and also magnetic properties. Maybe the last I will omit because of time lag. Let's start with the thermoelectrics. Thermoelectrics is an issue of our time because it's a renewable energy by simply combining two types of semiconductor materials on two pieces and two spots. You can make on one of the connections you apply heat, and the other connections you apply some low heat, as a temperature difference should be there as much as possible. Like, for example, the sun and the sun and dark side in a space lab, it has a difference of temperature of several hundred degrees. You can make a lot of current, and this is a renewable current or electric voltage. And now, in some applications, the difference of temperature cannot be done so well, so easy. So this is now the challenge to the materials physicists, to improve the material or the efficiency, the thermoelectric efficiency of the material, which is described by the feature of merit ZT. I will define in a short. Of course, you have also to take care that the material must be resistant to high temperatures. For example, in the space lab, it should be rigid for mechanical loading and should also fulfill all these conditions here. But there are already nice applications. For example, you can save about 10%. You can save about 10% of the car of the energy, which is normally spent to the electric system and to drive all the electric and electronic systems. And this can be spent by thermoelectric energy only. The feature of merit, this is the feature of efficiency, is proportional to the thermoelectric power, the temperature, because of the temperature in both cases, but it is reciprocal to the electrical resistivity of the material, and most important, to the thermal conductivity. So we can increase the efficiency by increasing the power. This is normally can be done by topological semiconductors. I will not concentrate in this presentation on this possibility. I will concentrate on the possibility to decrease the resistivity, but most important is the thermal conductivity. And the people in this community, they introduce defects because when we introduce defects in the lattice, in the materials lattice, in the crystalline lattice, it means that we can scatter the phonons. These are the lattice vibration, and that's why which hinders the conductivity, the thermal conductivity of the material. This is necessary to make this thing small. Yeah, so the thermal conductivity should be small. The thermal isolation should be high. The chemist people, they do it by introducing another materials of atom, as atom sort, the so-called doping or rattling atoms, and call the procedure filling. But we, the physicists, we are more interested, and this is also done by the chemists, introducing lattice defects. So far, it is already done that they introduce the grain boundaries. And our challenge is maybe we can introduce more defects, except foreign atoms. We can introduce not only grain boundaries, but also dislocations and vacancies, with the final goal to improve the ZT. This is the picture which is not normally shown by the chemists and used as a very prominent material, Skutterudite gold, which is a material like constructed the cubic structure TPN3 out of cobalt, iron, nickel on the one hand, and the phosphor, arsen, and antimony on the other hand. And you get the structure of the green and blue atoms. And then you add some special filler atoms, they are the golden atoms, which scatter the phonons more than before. And we have the idea, we use severe plastic deformation, why not, to introduce dislocations. You see here some single dislocations in the transmission electron microscope, and these dislocations arrange finally to these new grain boundaries. This is a grain boundary, and if you look carefully there, you see the single dislocations. So we are also here in the right order of magnitude. The size of the grains is now already, after plastic deformation, several 100 nanometers or smaller. And really, we had the big success when we were able to produce full crackless samples. This made necessary some experiments at higher temperature. We could make really full crackless samples from low deformation degrees to high, using high pressure torsion experiments. When you here see the feature of merit as a function of the temperature, it always has a little increase. This is the material with large grains, but when you decrease the grain size successively by increasing the deformation degree, you reach this curve and this curve. At the end, we are already here at the ZT of 1.4, and meanwhile, we reach the world record in Skutterudite feature of merit, which is near to 2, a factor of, a ZT of 2 in the N-type, and the factor of 1, and a figure of merit 1.5 in the P-type. So we are very proud of this fact. There is no other method which achieves bulk samples with that high ZT value. This is here the final goal, to get the thermocouple or a thermoelectric element. Here you see the increase up to this 1.9 ZT. And what is behind? Because the ZT consists, of course, of a low resistivity and a low thermal conductivity. Both at the same time is not easy to reach. And here, what you see here, the thermal conductivity decreases from before HPT to after 1 by factor 3. Then you see here in the resistivity curve at higher temperatures, the defects anneal, which is of course not so nice, because it also could mean that the thermal conductivity could increase. But fortunately, this is not the case. We lose a lot of vacancies. We lose also some grain boundaries, but still the lambda phonon, which is the conductivity, it goes down to high temperature. And this is the reason why we reach this very high ZT. But when we look in the electron microscope, we see everything except the dislocations disappear. And it comes out now that the dislocations are the units which are the most effective scatterers to the phonons. This was published by another group in the Wismut antimontellurid, other low temperature thermoelectrics material. And here you see low frequency phonons and high frequency phonons. The low frequency phonons are scattered by grain boundaries, only them. And the high frequency phonons are scattered by the filling atoms or the point defects, if there are any stable one. But the dislocations are much more effective, because they scatter, they decrease the kappa all over the whole frequency, because they have a dislocation core, a distorted one, and the less distorted but still distorted strain field. And with that, you see dislocations are really the best scatterers for the phonons, and that's why we are looking for producing thermoelectric materials by severe plastic deformation, exclusively dislocations, and look for new records in ZT values. Here you see again this picture. Dislocations can contribute to the scattering. When they are inside, there is the core and the strain field, and when they are part of the grain boundary, they can scatter at least by their dislocation core. Another title, which is also prominent in terms of renewable energy, because we produce our hydrogen as an energy carrier out of water with sunlight, also with light from sun, with natural sun by electrolysis, is how to get a solid hydrogen storage out of severe, by means of tools of severe plastic deformation. I only remind you that the hydrogen storage is in a factor 100 better in the energy density than all the batteries we have now. And on the other hand, and this is another big advantage, okay, we can store the hydrogen in a gas form. At the moment, it is the case with 700 bar, and with that you can reach with your car, if you have a nice car with hydrogen storage and the fuel cells, up to 600 kilometers, which is much more than with electric cars. But of course, you have a bottle with a high pressure of hydrogen. This is not dangerous, as some people believe, because you can make a very solid a container, which is rigid to 50 kilometers per hour crash. But the problem may be the volume. And we want to keep the volume small in the car, especially if we want to have individual private cars also driven by hydrogen energy. And the goal is to make solid storages which are efficient and can be done by technical production. And some prominent current storages are lanthanum nitride hydrogen and magnesium nitride hydrogen. Both of them can be loaded at room temperature, but they are heavy. So we have a problem with the weight percent of the hydrogen. We have to go to magnesium, and the magnesium has the little problem. It can be only loaded, or also the hydrogen can be absorbed or desorbed only with a minimum temperature of 300 centigrades. If you want to have a reasonable kinetics, you need a nice reasonable kinetics. You have to fill your tank within minutes, not in days. And for that, you need this temperature, and it comes out a nanocrystalline material. In the past, it was always ball milled material. Here you get a lot of grain boundaries, and if you have more pipelines for the hydrogen, you can load the sink very quickly, much quickly. But the problem is with 300 centigrades, you cannot keep this grain structure nanocrystalline, because in magnesium, there's a strong coarsening of the grain boundaries. And so we have to find another technique to make a stable process. One-time loading is not enough. We need several thousand of loading and desorbing and absorption of hydrogen to use your car longer than for one time. Okay, the question now was ball milling. Okay, we get a lot of powder, but if we need a lot of powder for our tank to get the ball milled nanocrystalline magnesium powder. But the problem is it is it oxidizes very easy. You have to produce this in vacuum, and have to keep it free from spoiling. And you have to keep it pure, and you have to get it nanocrystalline, which needs about 3 or 4 weeks to make ball milling. And this is a very expensive method. The idea was now, okay, not make bottom up or powder, take a solid nanocrystalline material and try to load it by hydrogen. It works very nicely. We made an ECAP test and found we can have the same kinetics, hydrogen loading in a short, several minutes, in the ZK60 magnesium alloys. The same performance it has like a ball milled powder. The next condition you need, as I already mentioned, is that you have to do this several thousand times. And the performance means the kinetics, the speed of loading, and also the weight percent, so the capacity of your storage should not get worse during the cycling. And for any reason, which I will explain in a short, is the SPD achieved material which may break later with higher cycle, achieves a high cyclic stability. So the material is also stable in their performance with the features 5% weight percent of hydrogen, and also in minutes loading after a cycle of 1000. This is true for the absorption and the desorption at the same time. And okay, we try to increase the kinetics and to increase the kinetics and also the storage, because we know the ZK60 has 6 weight percent, the pure magnesium may have 7. So that's why we tried not only the ZK60 alloy, which has a very perfect kinetics. You can do after 100 cycles as well as 1000 cycles in different SPD production methods, HPD and ECOP. You see it's the same. But if you do this with magnesium after a cycle 100, there is a clear deterioration in both the kinetics and the capacity. The question was why, and this question led us to the understanding of the process. What we did was a Avrami analysis of the formation of this hydride. Magnesium hydride is formed and deformed and resolved. And it seems with the ZK60, we got the Avrami exponent 1, while in the magnesium case, where we have the only pure magnesium, there is a Avrami exponent 3. It's typically in the double logarithmic mode, 1 line, and 2 lines in the case of the magnesium. It means, and this also went worse, it means there is only a nucleation process. There's no grow process of hydride in the case of ZK60, which is HPT-processed, while in the magnesium there is only grow. And what does it mean? When you have produced your defects by severe plastic deformation, which are represented by these 6 points here in some regular arrangement, you find out there is no nucleation at low and a low number of defects, because you make defects only in the first part. In the higher parts, you have high temperature and you cannot stabilize the defects. You have a poor number of defects, which can be the nuclei of your hydride formation. It means you have to make large bubbles of hydrogen, but this forms only very slowly because the diffusion of hydrogen in the magnesium matrix is very slow and very low. In contrast, in such an alloy, we did a lot of stable, high number of stable severe plastic deformation lattice defects, and they are stable against thermal cycling and thermal loading, unloading of hydrogen, and they are present because of these reasons in a very high number. It means you can make you nucleate your hydride phase, and you don't need to grow it because there is still the neighboring nuclei which let it grow, and they touch each other, and then you can fill all the volume in a very quick way. That there are severe plastic deformation defects, so defects from deformation, which are stable. It's shown and proven by DSC analysis. You can here see the annealing of the single vacancies, and here you can see in the DSC plot, this is the heat against the heating temperature. Here you see a clear indication of very large vacancy agglomerations, which are stable beyond 350 centigrades, and that's what we need. To sum up the last feature of the SPD functional materials treatment, the criterion for a good hydrogen storage, I can recommend you if you want to enter this field, easy nucleation of hydride phase, because and they can guarantee that by synthesis of stable SPD defect. You need a high density, you need these nucleation sites in the high density, and you should minimize the diffusion of hydrogen as long as it is possible, because it's very sluggish. And of course, the nucleation sites produced by SPD should be stable, and this is the case in the LON, not in the pure element. We can sum up. We found out that severe plastic deformation is a well-suited method to achieve bulk and 100% dense functional nanomaterials, not only such nanomaterials which gives high mechanical properties. And we see, it seems that the development, the research goes into the specialization to SPD low-dimensional crystal defects, because some of them, maybe dislocations and vacancy clusters, can be better in